Okay, good. So let's start with this webinar on this new module, CIVA Data Science. So thank you very much for attending this webinar. I will try to make a demo during let's say that it should last around 40 minutes. I will try to make sure that it will be not much not longer. And so I will start with a short presentation. So my name is Roman Fernandez from Exxon Company. Most of you or some of you already know me. But anyway, if you have questions after, don't hesitate to ask your question after this demo. So once again, welcome to this webinar. I will start. Yes, if you can mute, please. I will start with a short introduction to Extend, 2 slides, and CIVA, and then, of course, I will highlight the discussion and the presentation on this CIVA data science module. So just 1 slide about our activities for people who do not know us. So Extend, we are a French company with a subsidiary also in the US, Extend Inc. We are the exclusive distributor of CIVA. We do not develop CIVA. The CIVA software is developed by the French Energy Atomic Commission. So we are the distributor of CIVA. We also provide the technical support. And we also make, of course, training courses, so on CIVA and on reliability in ND.
I see you. I call you back.
Can you mute please, Jean-Michel? Can you mute your mic, please? Thank you very much. Yes, sorry for that. So we also make consulting. So we have a dedicated team at Extend and Extend Inc. that use CIVA for different customers, for qualifications, to design probes, for example, in UT, expert assessment, computation, and so on, mainly with CIVA, but not only. We sometimes use other softwares for benchmarking or also when we know that we are out of the limit of CIVA. So we use sometimes other software like Flux. And last point is that we also develop our own products. So it's not simulation software, but more simulator, I will say, trendy. So we develop this simulator, which are virtual training tools to train people in conventional UT and RT. So for training and skill maintenance. In a few words, for CIVA in a few words, so this CIVA is a software platform dedicated to ND simulation mainly, but not only, also analysis, and we'll discuss about that during this demo of CIVA data science. You can indeed also analyze real acquisition data from different systems, different acquisition in UT. And in the simulation part, CIVA deals with different techniques, so UT, and when I say UT, of course, I include phased array, TOF, tandem techniques, and advanced phased array like TFM. RTCT, eddy current, guided wave, structural health monitoring by guided wave, thermographic testing. And we have, since CIVA 2023, this add-on module, data science, that is linked to the script, CIVA script, so scripting capacity also in CIVA. And again, CIVA is developed by the French Energy Atomic Commission, the CEA. Regarding CIVA data science, so this is a very new module that has been integrated in CIVA 2023 in February and commercialized in February. The idea of CIVA data science is to offer the opportunity to use artificial intelligence in NDT. CIVA data science provides a global environment to combine real acquisition results and simulated data to design and evaluate machine learning based models for detection. We say here in this, combine real acquisition and simulation. But if you want, of course, you have a global environment in CIVA. If you want to just train your algorithm and evaluate them with only experimental data or only simulation, it's also, of course, possible. What is also interesting is that you can combine both, but you can do either only simulation, only acquisition, or both. The demo will focus on UT. but CIVA Data Science is compatible with other techniques. So it's also compatible with the different techniques that I shown just previously in the previous slide. You can create and manage databases, train and evaluate the AI model, perform automatic classification, and then test the diagnostic model with other data. The main reason why we have also this module in CIVA is that, of course, artificial intelligence relevance depends on quantity and quality of data used for the learning, so for training and validation. And we all know that real use of artificial intelligence in NDE suffers from the difficulty of getting sufficient and relevant data to train algorithm. This is, I think, the main problem, the main issue. So the idea again is to mix simulation and experimental data, and simulation can overcome the situation by efficiently providing massive relevant data sets with and without flow. This is the main problem of fortunately, I will say this is the main problem of in NDE is that we have a lot of data, but most of them are without indications. So this is the idea, and this new CIVA Data Science module allows you to bring together, again, CIVA simulations, CIVA analysis, and data management tools to design and validate machine learning-based diagnostic models in a global NDE environment and in the well-known CIVA platform. So you will see, we'll go, of course, more into details during the demo. I will try to go step by step during the demo to show you a little bit the environment and the process. But in few words, before going more into details, the features in CIVA DS are the following. You have database management tools, so you can collect, again, simulation and experimental data, but again, it can be only simulation or only experimental data. Merge the data, this is what I will show you. Define the relevant output criteria to train the algorithm. That can be also customized with scripts, with Python scripts. And then when you prepare all the environment, you can make the classification and detection diagnostic models. So to train machine learning tools on available data sets, try and set prediction and classifier algorithms. So we have different algorithms. You will also see that during the demo, and parameters. And then when you make the classification, visualize the classification results on relevant maps. So you have 2D plots, spread plots, confusion matrices, and at the end, test the diagnostic model on another data set. And again, this is compatible with all modules and works with CIVA script. So I insist, the goal is with the main issue is that few experimental data. So the goal is with few experimental data on a simple case, we use artificial intelligence to detect and classify defects. And to do this, and this is what I will show you. This is the logic of my demo is to add simulated data to the experimental one. So you will see in CIVA, when you will see my CIVA, I will start with experimental data. So acquisition, and we have acquisition with a zone with flow and a zone without flow. So at the first stage, we'll collect data from the experimental data without flow, all the simulation. So we'll add simulated data, build and merge the database. So the experimental data without flow and all the simulation that we performed. And the whole simulation and the experimental data without flow will be used to train for algorithm training and classification. So this is the first thing that I will show you. And then after that, we'll evaluate. So the evaluation will be done on experimental data that has not been used, of course, for the algorithm training to check from a known acquisition that the train algorithm AI gives relevant result prediction. So this is more or less the logic of my demo. And I try to explain a little bit here the different steps. So we'll start with the explanation of the chosen demo, so the experimental data and simulation that I will show you quickly. How to merge the data. consistency of our database, make the definition of the classification, and then the external evaluation. So this is more or less the logic of the demo. So let's go now directly into CIVA to show you a little bit that. So here I have loaded two experimental acquisitions. So what you see at this stage, I'm not yet on the CIVA DS module of CIVA. I've just loaded two acquisitions. So here we have two acquisitions on a weld. So we perform an acquisition on a V bevel of for part of 30 millimeter thickness of 30 millimeter. So we have two experimental data. The acquisition was done from two sides, so downstream and upstream from one side and the other side. So here what you see is from one side. So you have a scanning and you can see the different echoes. And on this data, we have a zone. We know this mockup. We know what we have inside. So we have three types of flows, and we'll focus the demo on the three types of flows: lack of fluid fusion, center wall flow, and a lack of sidewall fusion at the surface. So we have three types of flows. So you have the different echoes, and we have so a zone without flow. So we only have the dominical echoes from the root of the weld, and the zone with the flows. And again, from both sides. So you have on the left, you can see the two acquisitions. We call that Z2 and Z1. So you have one acquisition from one side and another acquisition from another side. Before going more into details on the acquisition, I will also load some simulations. So we perform also 8 variations, so a lot of simulations with 8 parametric studies. So you know that in CIVA, we can perform a lot of simulations and make a variation on different input data. So here, this is one example. We model this defect and the response of this defect by defining a lot of different variations, so 400 variations. So we have here in the version panel all the variables. So we make variation on the thickness of the part, on the orientation of the flow, the positioning of the flow, the tilt angle of the flow, and so on and so on. So 400 simulations. And yes, Tumelo, I see that you have raised the hand. If you can ask your question after the demo, please.
Okay, yeah, no, it was just to ask if you can maximize your screen. That's all, the CIVA one, because I mean, to me, it's a little bit far. So if you can maximize it, please.
I'm in full screen. I'm sorry, I'm in full screen here.
On CIVA.
Yeah.
Okay. Thank you.
Sorry. You're welcome. Yes, so here this is the variation, one example of variation where we perform 400 simulations. The idea is to add a lot of data to train the model. So it's just to explain you a little bit the procedures before going to the CIVA DS module. So we run 400 simulation on this case with scanning, and it's important, you will see after when you will see the CIVA DS module, scanning of 86 steps. So you see my probe that is moving, 86 steps, the same scanning step as we perform in the real acquisition. So we perform B-scan here with these variations. So one here with this flow, and another example here with another flow and other variation. So it was to prepare everything. So we have the 8 variations, 8 files, and in every variation file, 400 simulation. So we perform as in real, as with the experimental data, simulation on one side of the weld and simulation on the other side. So last point before going to the DS module, I just go back to my experimental data. You need to prepare the experimental data. The reason is, and you will see that just after, you cannot, in the CIVA DS module, you cannot directly load the full experimental data. You can just load binary files. and you need to export the experimental data and reload it in the CIVA DS. So the first step, and I will just show you in one case, not of course not in the two experimental data, it will be a little bit too long, but the first step is to prepare the acquisition, the results, thanks to CIVA Analysis. So here I'm in CIVA Analysis. You can perform, people that already know CIVA Analysis, you can perform some limitations. So just as a reminder, we have two zones in my experimental data, one zone with my flows and one zone. I think someone mute me. It's okay. Do you hear me? Yeah. Hopefully you can. Yeah. So this is my experimental data, and again I will split this experimental data in two sets of data: one data set with my flow and one data set without my flow, so with only the geometrical echoes. So in CIVA you can make a limitation. So this is what I will do here. Define, this is this blue option, define a limitation, where I will split the data. First of all, I will make a limitation on time, so on the depth. You see, you have here, we are saturated because we record the surface echo. So I will just split the data in time or in depth. Okay, so here you see my global C-scan with all the echoes, so geometrical echoes and the echoes from the flow. And as I said, I will make two limitations, one with the flow and one without the flow. So no flow will be the training set with a given limitation here. I know the file. So here from 250 to 240. Okay, so here I have just my geometrical echo. You can rename the data set. So limitation, no flow. Okay, and the idea is to do the same thing. So I come back to my raw data to make a new limitation. Again with the same depth. And in my increment, I will just focus on the set including flows. So I have now my two limited data. Here, this one I can also rename it. This data limitation with flow, if you remember the presentation, I will use that to evaluate at the very end of the demo. So, because, and this is what I said a couple of minutes ago, the experimental acquisitions cannot be directly imported into the CIVA DS database. So we need to export it into a binary file. So on the top here, you have there is on the top here. Sorry, there is cannot. Yes, on the top here, if you see here on the toolbar, there is DS export. So the idea is to export the data, so the C-scan, the limited C-scan, into binary files. So in CIVA, it's called CCK files. And so the binary files we generate it's a generation from experimental results with one output corresponding to the amplitude information. So you have here some parameters to key in. So we'll not go into details, but it's some parameters to say what output. This is important to train the algorithms after, to say on which data you want to train, if it's only the maximum amplitude or the echo dynamic or the time of light and so on. So you have different options here to define if you're going to export which information you are going to export to then re-import in the CIVA DS module. So just one word about that. If you select loop over, that means that each value of the increment, for example, here, you will each value of the parameter generate new sample. So we have given number of increment, so we'll have new samples for every increment. Known, that means each value of the parameter generates a new value for the output. And I will show you and explain a little bit what is in CIVA-DS the output. And max is the value of the output. The value of the output is the maximum value for this parameter. So you need to define what information you want to extract. Okay, so define different information here, and then you just apply. And at this stage, so it's a very first version of CIVA-DS. So for now, this CCK file is automatically saved on the desktop. Unfortunately, you cannot select where you want to export it. And if I just show you my desktop, you have this export CCK that has been created. And the idea is to re-import them in the CIVA-DS module. So I will not do it for all the four experimental data. So just again to remind you, we made two experimental data from the two sides of the weld, and then I create limitations to define the zone, my zone without flow and my zone with flow. So it will be four acquisitions at the end. And then the idea is, once you export everything in these binary files, is to go to the desk and you have this data science module and to define everything. So we'll close this. For people who already know CIVA, so you have on the top the different techniques, UT, guided wave, eddy current, and so on and so on. And in one given submodule, you have in one given module, you have some modules. So in UT, you have the beam, simulation, inspection simulation, the parametric study, the POD, and so on. The logic of CIVA data science is the same. You have some modules, and in few words, the idea is, I will try to explain you in few words what are the idea of the different submodules and the logic. If I just go back to my slide, the idea is, first of all, to collect the data. Okay, so this is what I will do right now. So you need to collect the data, you need to click on database and meta model. So the idea is to collect simulated and experimental data, define the output criteria, generate meta models, why not, if you want, and check data dimensions and consistency. The database fusion, this will be my second part of the demo, is to merge the different data. If you remember, I have experimental data and variation file simulated data. So to merge and to define the relevant output, so the result obtained for the samples input that are represented by a vector for each sample. You can use Python notebook, so you can use Python script to customize datasets to your needs if you want. Again, CIVA data science. So then you will use the classification to define the target classes for the defects to be characterized, make the pre-analyze, and make the different options to see the classifier and if it works or not. And finally, to evaluate the diagnostic model on external datasets. So again, this is what I will show you. And you have two other options: outlier detection, that is, let's say that to train the model with one class and set the threshold for success failed evaluation. So for example, it can be, for instance, flow or no flow detection by training it on no flow database. And the prediction accuracy, let's say that it's more related to only simulation and meta models. So to evaluate the accuracy of the meta models you generate from the databases and simulation variation. So let's go to my database and meta model. So here I will create my new empty data science project. So let's put it CIVA DS webinar. Okay, and so here I'm in my DS module, and the idea is at this stage to create the database and to load the binary files that I export. So we have the binary files here. You see that I have different inputs and outputs. Okay, so we defined when we export the binary file the ecodynamic, and you see the shape here, it's the number of scanning steps, you remember, 1 to 86. And for one given experimental data, you have the ecodynamic and the different scanning. So we have here my experimental data. So at this stage, I will make a fusion because we have, as you have seen, we have experimental data from both sides of the world. So the idea is to make a fusion to say, okay, for one increment, we'll make a fusion of the ecodynamic. So I will show you that. So it's just some manipulation. I'm just putting on the good order. And then, so I will also show you after for the simulation. So here I'm just focusing on the experimental data. So I have my 4 sets, and then database fusion, create new fusion in current DS. And I'm going to make a fusion from the 2 sides of the world on the part with the flow. So here I can change the name, experimental data flow. On the top, you have different drawing type to define the fusion models. So the fusion module offers 3 data merging type. Again, I will not go into details, but it's to define which outputs you're going to combine. So here I'm just going to go to data aggregate. You will see that I will have at the end 2 outputs. So you have on the here inputs, this is my file, and outputs, the ecodynamic, the export signal. So I will define here the output, and then you need to adjust a little bit. Because we'll have 2 outputs, I just need to change the tag. The tag is just a label to be consistent with the logic of this data aggregate. I can test it. Okay, so I have now the fusion of the 2 sides of the world with on the limited data that I made with the flows, and I apply. So I have my fusion here. So you see I have a new ID file with my experimental flow. I can remove these 2, and after I need to do the same thing for the zone without flow. Let's do it again. I will try to do it quickly. Experimental, no flow. Same drawing type, of course. I will use these 2 here. Test it and apply. Okay. So the idea is to, after that, I will repeat the same logic with my simulation, with my variation files. Before loading and making the fusion of my variation file, there is also one thing that is important, and for CIVA users that use CIVA UT in both simulation and experimental data, you know that the calibration is important, and when you run a simulation, you have what we call the amplitude in CIVA points, and when you load experimental data, the amplitude in points is not the same. So there is an additional step when you want to compare and to merge experimental data and simulated data is calibration and normalization. So to be comparable, simulation and experimental database should be calibrated. So we performed that. We did that on a backwall echo. We took 0 dB and we compare the values in points, CIVA points, and the values experimental data. And we found, in this example, the normalized factor. So we need to apply this normalization. Yes, Eddie, I will answer you to your question after the demo. So here we have we need to make the normalization. So to do that, we just need to, in the outputs, to add outputs. And you see here that you can define formula. And the normalization in that case is this value. And you can also dispatch, so I will apply this normalization on both data, experimental flow and no flow. So I have this. Sorry. I made a mistake. You see, I made a mistake. I put 0 and not. So I will just remove it. I will do it again. Output. I will add it. It's 0 and not O. Okay. Okay. So I have one additional tag, and I will again add another output, which is O2 divided by. Okay. I'm just making some manipulation to now we'll keep this new data that has normalized to my simulation. So I'm just going to remove the two others. And also for this one. And last manipulation that I need to do is also to rename, because we need to have the same label. The tag is a label between my simulation and my experimental data. So I'm just going to rename this one. And yes, again, I made a mistake. And O2. Okay, so at this stage, after that, so here it's okay. Then I'm going to my database fusion, and I'm going to load I'm going to here to load my version files. So you can load the version files and make again the fusion on the version files. So I'm doing this. So it takes some time. Okay. And I will just keep the economic scanning, because in the output for the data, I have only my economic scanning. So I will remove the economic time. Okay. Then I can again remove this one and this one. Sorry. Low. Just reloading this. So this is a procedure that you need to, of course, to take time to prepare everything. Okay, this is my one, my two. Okay, so I have my experimental flow, experimental no flow, my fusion with my my simulation of this flow like of root. And then again, I need to do the same thing for my other simulation. So I will do it very quickly. Okay, this one. No, sorry, this one and this one. And the last one is my simulation without flow. So where we just simulate the backward echoes. Tac. Okay, so it took it some time, but I wanted to show you step by step, and this is the reason why I did it without loading a pre-calculated file and predefined file. The idea again here is to merge the data and to prepare everything. And you see that we have here the different samples and the shapes. And for every fusion, we make the fusion on both sides, Z1 and Z2. Here, these are my simulations. So we have the variations on the different inputs, the different variables we define the simulation. And on the experimental data, you have also the table with the index, and the amplitude, and the two outputs, O1 and O2. And again, all these manipulations that I made, you need to be consistent. That means to have the same label, the tag, what we call here the tag, O1, O2, for every data. So this is the reason why I changed the tag and I made this manipulation. So just it was just to explain you a little bit what I did. And on the right, you can see the different results, the tables with the different results on simulation and experimental data. So to sum up, after some manipulations, so normalization of the data between experimental and simulated, same output vectors. These are the output vectors with the same physical quantities. So here, this is the economic scanning with the amplitude. The idea is after that to perform the classification. So let's go back to the desk and we can go to the classification. You have, again, here a reminder of the databases with the different fusion. Okay. And the idea is to train the algorithm. If you remember the presentation, if I just go back here, so we are on step 2, we check the consistency of our database, we make the fusion, and the step 3, definition of the classification and training of the model. But of course, we are not going to train the model with the experimental data with flow. So we're going to train the model with the experimental data without flow. So one real acquisition with the data without flow, and all the simulation. So we add the simulation. So I'm going to untick, where is this one? My fusion experimental flow. Okay, I will not use this data for the training, for the classification, and I need to define the classes. So you can also import a file, but here we'll do it manually. So you can change here the no flow. And this class, you need to have the same name in both experimental data without flow and simulation data without flow. This is the same class. And then I can here define, this is a lack of root fusion, lack of sidewise fusion, and this flow. So we have here 4 classes, 3 different classes of different flows at different positions on the weld, and 1 without flow. And I will train my algorithms on this data. And again, I remove the fusion experimental flow. So here I click on apply to initialize the classification. So it takes some time to load and to prepare the classification. And on the right part, you have different options. The first thing that we see here is the parallel plot. It allows to customize the display colors and lines parameters for the classes. And you see that we have all the samples here that we used for the classification, 1646, which correspond to the 400 simulations for the 4 files, plus the 46 from the experimental data. So we have all the different data, 1646 data. And the other thing that we can check also here is that we can see that all the samples have comparable maximum amplitude values, which mean that we correctly calibrate. It took time, and this is what I did 5 minutes ago when I divided by 20,000 to calibrate my experimental data with my simulated data. The second tab you see on the top here, so you have the parallel plot, and then the second tab, sorry, is classifier. So for the classifier, you have 2 options, the 2D analysis and the classification. So let's start with the 2D analysis, just to show you. I will split, so we have here the projection method. You have different projection method here. I will keep this one by default. So the UMAP, uniform manifold approximation and projection. So we see the general purpose manifold learning and dimension reduction algorithm. And if I click on split data, we are going to have a first, let's say, pre-analyzing. So it's a 2D, it's quite simple analyzing. It will not be used for the training, but the idea is to just make some tests to see if we have enough data and if the data are relevant then for the more complex classifier. So just to check if the classification has a chance to succeed and define proper parameters for the training. So the idea here, we define the test size. You can also change the test size. That with CIVA splitted the data with 40% of the data to train and the 60% remaining to test. You can change that. So the splitting step allows to find the best way to separate samples in the defined classes from their output. So it's a 2D analysis here, and you see that you have dot points that are the train data and the squares that are the tests. And you can see here that you have different zones just to see if we are quite good or not that good with color codes with the different classes that I defined, lack of root fusion, lack of sidewall fusion, no flow, and the last SWC flow. And you can see the different points. So this is one thing, the 2D plot. And you have also the so-called confusion matrix. So CIVA offers some analysis tools as the confusion matrix. You see the confusion matrix available in the second sub tab. So for expert in AI, I think you know much better than me, but you know well this confusion matrix. The idea is to make sure that between the true labels and the predicted label, we are okay. So of course, the ideal result would be 100% along the diagonal. Okay, so with the true label and the predicted label. And you can see here that we have some confusion between the root fusion and no flow, which is, I think, quite logic. And the last point is that you have also the parallel coordinate, which is more or less the same thing than the same information as the matrix of confusion, but with color lines, with the prediction and the classes. So anyway, here, this is just 2D analysis to prepare the final training and just to check. The idea after that is to go to the classification. So let's click after 2D analysis. You have the classification training. So if we go to classification, you have here different options to optimize the different components and select the algorithm to define the different to train the class. Mute again. Okay, I was mute again. So you have the different options here for the different parameters. For the scalar is a kind of automatic calibration. Okay. By normalizing values according to the max or to the min max. So we have different options here. The projection method, so PCA or UMAP. And so here we'll keep the default result and we click on optimize and components. So here you see that the optimization with the projection method finds 66 components, so 66 dimensions to get the best results. And if I click on fit and evaluate classifier, we'll see the new confusion matrix, but not with the 2D, but with the 66 dimensions. So you have here the new confusion matrix that gives better results than the 2D plot, 2D analysis, with still some confusion here. So again, we have this main confusion is between the lack of root fusion and the no flow, but it's much better. So here, this is how to proceed and how it works to go to the classification on so we use to train the algorithms. I repeat, we use all the simulation and the experimental data without flow. Once we did that and we are satisfied by this, we can also make the evaluation, and it's let's say that it will be the final step in this demo to make the evaluation. with external, so it's the external evaluation. So the objective, if I click on external evaluation, the objective here of the external evaluation is to check, to verify from a known acquisition. We know the acquisition and we know what we have inside. So from a known acquisition, we know, so again, the type of defects and the positioning, that the trained artificial intelligence model is able to correctly detect and predict the origin of the indication. So I will load here my experimental data with flow, and I will define the annotation. I know the annotations that correspond to the non-flows position in the experimental data. So this is what I will do here. We know that it's just to evaluate. Okay, so we define here, and then we apply. And we have here a parallel coordinates here to evaluate. And if you have a look, you have here the annotation, the prediction, and the probability. So you can evaluate and draw some borders to see if it consists, if the prediction and the annotation it's consistent. And we can check that if the train AI algorithms works with my experimental data that was not used for the training. So you have here the parallel coordinate to check the consistency between the annotation and the prediction. Here the samples, and on the right also the probability. So we can see that we have overall quite good result with, again, sometimes some mistakes you see here between the annotation and the prediction. It's not perfect here or here. If I just click here, you see that you have also some confusion between the lack of root fusion and the no flow, especially at the edges here. But the idea is again to compare all the data together. And so you have here again the different indexes, the annotation, the prediction, and the probability, the confidence degree of the algorithms. You can also, if you want, export results, and you have here some algorithms, but you can also, with a Python script, input some algorithms if the one that you want to use for the training, for the machine learning, are not the ones that are in CIVA. So it's this is more or less the logic and the idea of this CIVA DS module. It took some time. It took me some time at the beginning to make the fusion and the normalization and so on. But the idea was to show you the step by step and the procedures to train again the algorithms from a set of data by mixing some simulation data and experimental data, and then evaluate, test the algorithms with another experimental data that, of course, I insist, we not used on to train the models. Thank you for your time. So I will have a look on the question and answer through the chat. So I hope it was clear. It's not that easy to explain, but I hope it was clear. So I will just open the chat menu. to see. Yes, so one question from Mr. Boyd, Eddie Boyd. What's your performance on composite materials with the CIVA DS platform? To be honest, personally, I never test this data science and composite, but I don't see any limit as soon. This is always the same problem, limit or problem. If you want to merge experimental data and simulation, you need to make sure that you are in the limit of the models. As soon as you are in the limit of the models, I don't see any reason why it will not work. The idea is the same, and you can train the data. You can train, sorry, the algorithms on some data and then test them, but I don't see any reason why it will not work. And again, if you can use CIVA DS only with experimental data or only simulation. Here I show you what I show here is a mix, a fusion of experimental data and simulation. But you can, if you have enough experimental data, you can in CIVA DS just use this module
Okay.
on experimental data or only on simulation. Jean-Michel, I think you have a question, or you raised a
Yes. What is the Python notebook exactly?
It's a script. So you have a notebook. You have in CIVA. It's not only for CIVA data science, by the way. You can script in CIVA in the simulation and also in CIVA DS. You can script almost everything in CIVA. The first idea, if I don't talk about the DS, the idea is to have CIVA as a kind of black box. That means that you can define some inputs by script. You can make some changes, some variations, even make loops, iterative loops to converge on a given result. And you can also export everything without opening CIVA. And then you can
in this we are able to write one application in Python to charge to load in DS. These things.
Yes.
Okay. Yeah. Okay. Thank you.
So yes, CIVA DS, it's an add-on. So you don't have, by default, you don't have this module on when you use only CIVA UT or only CIVA eddy current or only CIVA RT or the other modules. You don't have by default CIVA DS, and also you don't have by default CIVA script.
Okay, it's clear. Thank you.
You're welcome. Of course, this is the very first module of this CIVA data science. So we all need to test it, to make sure that it's consistent, to check the algorithms, to train them, to evaluate them, and so on and so on. So I will say it's the beginning, hopefully it's the beginning of a long story of artificial intelligence in NDT, thanks to CIVA, and again, thanks to why not combining experimental data and simulation to have more data, to increase the number of data to improve the training.
Okay, it's clear. Okay, thank you.
You're welcome. I don't know if you have other questions, again, through the chat, please, if possible. I don't know if it was clear or not. I will wait some seconds more to see if you have other questions. There is a question about what are the respective class scores. So I'm not sure to understand, but if I just go back here, I'm just trying to have access to my CIVA. I need to move this. Yeah. So here you have the score. You can have a look on the score on the evaluation. So you can have the score for the different results. So be careful. It's not 22%. The score is not 22%. It's you have a different samples with flow. Okay, and you have a given score that is not 27 over 121, but it's just you have different data with no flows, and you have a given score that you can have a look here, and you see here that we have some mistakes. So for example, 12 wrong, let's say wrong results. So you can check the score with this algorithm with these inputs. So this is the evaluation. But of course, again, everybody, I think we need to test them and to make the score on their data to validate that.
I have a question on the calibration file that you did to normalize your data.
Yes.
Was say on a side drill hole or a flat bottom hole calibration standards, and you wanted to do a DAC curve, is that possible within your
Yes,
the
definitely.
file that you applied there?
Definitely, you can do that. This is, let's say, the CIVA process. You always need to calibrate. When you run one simulation, you will have if you run one simulation and you will have a result on the flow, you will always need to calibrate this result on a side drill hole, on a DAC, on a flat bottom hole. You will do the same thing with your experimental data, and you will have one reference. For example, I took as a reference the backwall echo, but it can be the side drill hole. You will run one simulation and one experimental data on one side drill hole. You will say, this is my 0 dB, and you will see behind the dB you have some values in points, and you will adjust and you will normalize the result and then apply to all the data. This is what we did here.
Okay, so you run and do it in the simulation, and then you run it in the tank and you get that data. And what we have found, we've trying to match it up with the spherically focused for what the best parameters are to run, but we still sometimes are like 6 dB off from real life data. So what that's going to do is if we use this, it'll help normalize to bring that closer together, the real life data to the experimental, to the CIVA data, right?
I'm mute. Sorry, I'm mute again. I don't know why. Do you hear me?
Yes.
Yeah. Yes. Sorry, my question was, you mean that you have 6 dB differences on between your experimental data and your simulation?
Sometimes it's more, sometimes it's less, and we try and narrow that down as much as we can by playing with the radius on the spherical radius, just to get them as close as we can together.
If you have 6 dB difference, it's not normal. So either there is a problem in your simulation. We can check. You can send your file through to the support, or maybe a limit of the model. I don't know, but 6
Okay.
dB it's a lot. So
That is okay.
this must be investigated. Of course, if you have.
You're muted again.
I really don't know what is happening. I'm very sorry about that. Of course, if you have discrepancies between your experimental data and your simulation data, if you merge everything, if you merge experimental data and simulation data, the trained algorithm will you will have some very false positive or false negatives and discrepancies also in the AA. So this is something that, as everything in CIVA, before going to more complex things, you need to check and to you and I include, of course, extend. We need to understand why you have such difference to go further. So if you can maybe send your simulation at least to check if we
Okay.
are on the limits or whatever.
Yeah, we can do that.
Yes, there is another question. What are the limits and perhaps future improvements? It's a good question. So the limits up to now, difficult to answer. It's a very beginning, so it has been tested and validated on some cases. Here in this case, it works pretty well. It's a quite simple case. Conventional probe T60. But this need to be improved and tested by us, by the CA, by the ND CIVA community. So it's difficult to give you an answer, an accurate answer. And the other, I'm not sure it's a limit, but the other, I would say, target and goal and challenge. Another challenge is in additional cases. So in this case that I show, it works pretty well, but it's to make sure that the combination of the simulation and experimental data does not bring some mistakes. That the algorithm correctly understand the data and will not have discrepancies because we merge real data and simulation data. So this is one point that is very challenging. We want to test it. We want to validate that. And I think that CIVA can help a lot for that. The idea is the same. It's always the same. We don't have enough experimental data with flow, with indication for the machine learning to train. So the idea is to increase the data with simulation, but we need to make sure that the algorithms correctly merge both data from simulation and experimental data. And this is the thing that we all need to do. The future dev improvements, probably other algorithms, neuron, what's the name in English? Network of neuron. I don't remember the name in English, sorry. But to have other algorithms more robust and again to test that. Neural network, I think. So I don't know if there are other questions. I don't see any other questions here. And of course, last point is that with Python you can also plug your other algorithms. Anyway, so I think we can stop the webinar. Thank you very much for your time. I really hope it was clear. It's sometimes difficult to mix ND with machine learning, but I did my best to explain you as much as I can. If you have questions, feel free to contact us, of course, either from the support if you have technical questions, or to me if you want. So you have my email address here on this slide. So don't hesitate to contact us if you have some questions, if it was not clear, and if you want more information. Thank you very much for your time, and goodbye.